So we just talked about the timer interrupt that lets a kernel control the user code. And one thing that a kernel might do is, when it gets that interrupt, switch the current user code out of the running context and bring some other user code in. In other words, it might be running one program and every once in a while start running pieces of a different program. And then when the kernel gets another interrupt from the timer later, it might just say, okay, that program has had enough time, and swap the other program in. This swapping among different sets of user code is called a context switch. So that's why you're able to run two programs at the same time on your operating system, because it periodically switches context between the two programs. And for this to make sense, each of those programs needs to each of those user bits of code need to carry alone its own bit of memory. The program that's currently running on the CPU gets to use the CPU's registers, but when the kernel swaps a program out, then it needs to store the registers that were in effect when the program was running, so that when it resumes through a future context switch this old program, then it can restore those registers to the CPU. Now, we know actually that the program itself is stored in memory somewhere, and when a kernel is doing a context switch between these different programs, it's really just moving things around in memory somehow. In fact, it would prefer not to copy things out of one memory into some other memory, and so on. So a process is an instance of a particular program, so it's going to have some memory and some registers as it runs. And each process gets its own local control flow. The normal control flow for each individual process is separate from the normal control flow of others. So the illusion that a program sees is that it seems to have access to the whole CPU, when in fact, behind the scenes, the kernel is swapping things around. It also seems to have all of memory itself. Your process doesn't see this view where there's some memory packaged up with a particular bit of user code, which is different from some other memory. The kernel manages things so that each process seems to have all of the memory that there is to be used. And so another way to draw the picture is, from an individual program, there isn't user code and kernel code and so on. There's just the program with its memory, its stack and its heap, and its code, and it's running on a CPU that has registers. But in fact, this process view is just an illusion. Many other processes running at the same time seem to have the same view of the world. They all have all of the memory, and they're running on the CPU. What actually happens is that each individual program is put into the same memory, the physical memory that your computer has, but only one of them is running at a time. One of them, its stack and heap and code, are mapped by virtual memory, the virtual memory mapping, made active, so that when various addresses are used by instructions, they access the particular part of memory that refers to that process. Also, each process has a little room for saved registers, so that when it's time for a context switch, then the current value of the registers can be copied into that space in memory, and then we can switch to a different process, copy its saved registers back in, and start running that process. This is what happens when a computer has a single core. Then there really is just one CPU, and it has to be shared among different processes. If you have a multi-core machine, the picture is basically the same. It's just that more of these processes do actually get to run with a CPU at a time. They're all in the same memory, and each CPU has its own view of how addresses should be translated, so that each one can be running a different process.